Myself, Shafra Sultana. Today my topic is random process. Introduction to random processes. In linear chapters, we studied probability theory, how we deal with uncertainty, random variables, variables whose values are not fixed but depend on chance. Now we move from random variables to random processes. Definition of random process. A random process is also called as stochastic process. Is a collection of random variables that change with time. And next one, in simple terms, it is a time varying random signal, or it also called as, and it also read in this definition of a random process is a time varying random phenomena described statistically using tools like PDF, small PDF, probability density function, or probability distribution function, correlation, and covariance, which help us understand and model signals such as noise and message. Signals in communication system. Examples: message signals in communication, background noise in a receiver, variations in weather like temperature or rainfall. Why do we use random process? We use random process to study signals that change unpredictable with time, such as noise or message signals. We cannot fully know their behavior, only their statistical properties like the average power, variance, etc. can be known. Hence, they are described statistically, not deterministically. Different forms of a random process. When time t is fixed, you only look at a particular instead of time. The random process becomes a random variable because only randomness remains, represented as x of x comma t1. This shows the random value of the process at time t1. Example of different forms of a random process when t is a fixed. Noise voltage measured at one instant but may different each time you repeat the same value. When the sample space S is fixed, you are only at one particular outcome, one experiment. It becomes a real function of time, represented as x of S1 comma t. This means for one specific experiment S1, how the signal changes over time. Example of when the sample space S is fixed. The waveform of one realization of a random signal, like one recording of the signal. This is only example for the when the sample space S is fixed. When both time of t and sample space of S are fixed, both are given specific values. So it becomes a constant, represented as x of S1 comma t1. Example of when both time t and sample space are fixed. The value of a signal it is specific instead of one experiment. Conditions, there are four types of conditions are there. First one, time variable and sample space variable. And next one, time fixed. And another one, simple fixed. And last one, both fixed. There are four types of conditions. And now we can discuss the four types of representations, nature and example. Time variable of representation or sample space variable. Time variable and sample space variable representation, capital X of S comma T. Nature, random process, and its example, random signal. And next condition, time fixed. And time fixed representation, capital X of small s comma t1, and its nature, random variable. And its example of time fixed. Noise at a particular instant. And another one, sample fixed of condition. And its condition of sample fixed and sample fixed representation is capital X of S1 comma T and sample fixed nature time function and sample fixed example is one noise waveform. Both fixed of representation x capital X of S1 comma T1 and it's thus both fixed nature constant and both fixed condition of example is single value of a waveform. Now we can discuss classification of random processes. Random processes can be categorized based on whether time and the amplitude of the random variable are continuous or discrete. Accordingly, they are divided into four main types of classification of random processes. Now we can discuss first one. Classification of random variables is first one, continuous random process. And first one, a random process is said to be continuous if both time and the random variable are continuous over the entire duration. In this type, the random variable can take any value within a continuous range for all moments at time. And next one, example of continuous random variable. And its example is the fluctuation of noise voltage in an electrical circuit where both time and amplitude vary continuously. Now you can see the diagram of some ample function of a continuous random variable, and they have so many amplitudes are there and different types of amplitudes, and they are consists of time and random variable. They have so many different waves in the amplitudes of the diagram. Classification of random variables in second type of discrete random process. In a discrete random process, the random variables take discrete values but time is continuous. The random variable gets switched only between certain fixed levels while time progresses continuously. For example of discrete random process. Example, a digital signal that alternates between two discrete levels such as positive and negative level but exists continuously in time. Now we have to see the diagram of sample function of a discrete random process. They have amplitude and the time. X-axis time and y-axis amplitude is there. And we have to represent the levels of the positive level and the negative level to execute the continuously in time. We have to discrete time in continuous and they have to move the positive and negative levels but exits continuously in time, and they have to alternate between two discrete levels, such as positive and the negative levels, but exits continuously in time. Classification of random process in third classification of continuous random sequence. A continuous random sequence occurs when time is discrete, but the random variable is continuous. The random signal is defined at specific time intervals, but its amplitude can take any continuous values. It is represented as a set of random variables defined only for discrete sample instance such as tk equal to 0, 1, 2, and they have so much values are there. This type is often used when sampling a continuous signals without quantizing its amplitude. Now we have to see the diagram of sample function of a continuous random sequence. They have to move the sequence of waves, and and the x-axis is represent the time, and the y-axis they have to represent the amplitude. We have to move k equal to 0, 1, 2, and so on. They have to some random variables are there. Random variables and discrete sample instances. They have to sampling continuous signal without quantizing its amplitude. Now we have to fourth one discuss discrete random sequence. In a discrete random sequence, both time and the random variables are discrete. The signal is sampled at a discrete time intervals, and the amplitude is also quantized into discrete levels. This process is commonly used in digital signal processing. The amplitude may be represented using two levels or multiple quantized levels, depending on the application. It is often obtained by both sampling the discretizing time and quantization discretizing amplitudes. Now we have to see the sample function of a discrete random sequence. They have two discrete time levels of x-axis and the y-axis represent the amplitude. We have to quantize it into discrete levels, and we have to obtain the signals is discrete time variables and discrete random sequence. We have to move to x-axis to y-axis. They have to positive levels and then move to the negative levels. Classification of random process. There are four types, both based on the whether time and the random variable are continuous or discrete. We classify random process into four types. They are first type continuous random process, and next one discrete random process, and another one continuous random sequence, and last one discrete random sequence. Now we have to discuss four types of random process in classification. Now we have to discuss first one continuous random process in time variable continuous, and next random variable continuous. An example voice, signal, thermal noise. And next one discrete random process, we have to time variable discrete and the random variable continuous. An example of discrete random process, daily temperature readings. And another one, continuous random sequence. The time variables of continuous and the random variable discrete. Now we have to discuss continuous random discuss example. Switching between discrete state continuously. And last one, discrete random sequence. And the time variable discrete and the random variable discrete. The both discrete are there. And the discrete random sequence example of digital data, coin toss, outcomes at fixed times. They have to four classification of random processes. Sampling converts the continuous time signal into discrete time values. Quantization converts the continuous amplitude into limited number of discrete levels. We have to see the sampling function of a discrete random sequence, multi levels they have. Now we have to discuss see the deterministic and non-deterministic of random processes. Deterministic process. A deterministic process is one in which the value of the signal can be exactly predicted at any instant of time. Once the mathematical expression described it is known, there is no uncertainty in the behavior of the signal. Every future values is completely determined by the known function or parameters. Example of deterministic process. X of t equal to 5 sine of 2 pi 50 t, a pure sine wave whose values can be computed exactly for any time t. X of t equal to 3t plus 2, a straight line function with a predictable values. And the deterministic process of characteristics, predictable and repeatable. And next one, no randomness or statistical variation. The last one can be described completely by a mathematical model. Now we have to see the non-deterministic random process. A non-deterministic random process, also called a random process, is one in which the value of the signal cannot be predicted exactly before it occurs. The signal contains uncertainty or randomness. Only the statistical properties such as mean, variance, correlation can be discussed. Now, exact values. Example of non-deterministic process. Thermal noise in an electrical circuit, and next one, atmospheric noise in communication systems, stock market fluctuations, and non-deterministic characteristics are there. Not exactly predictable, only probabilistic information is available, described only probability density functions or statistical averages. Each observation or realization may different even under the same conditions. Now we have to see the features, deterministic process, non-deterministic of random process. It is first one, feature, predictability, representation, repeatability, example, uncertainty. We have to see the deterministic process, non-deterministic random process. First one, predictability of random deterministic process completely predictable. Non-deterministic of cannot be predicted exactly. And next one, representation. Deterministic process, exact mathematical function. And non-deterministic random process, they have to statistical description. And next one, repeatability. They have to random process, same output for same. And non-deterministic random process. Different outputs even with the same conditions. An example of deterministic process 5 sine 2 pi 50t. And non-deterministic process of example thermal noise random voltage. And last one, uncertainty, deterministic of none. And non-deterministic random process, they have to present. Independent random processes. Single process independence. Consider random process x of t. Let x of t I equal to I equal to 1, so on capital. Be random variables at type instant t1 so on tn with density function fx of ti of xi. If x of t is statistically independent, the nth order joint density functions equal the product of individual densities fx of t1 and so on x of tn x1 so on x of capital equal to fx of t1 x1 of into fx of t2 x2 so on fx of tn of x of capital N. They are independent random process. Two processes of independence. Consider two random processes x of t and y of t. X of t has random variables x of t1 so on x of t of n with joint density fx of t1 so on x of tn so of x1 so on xn of t1 so on t of capital y of t has the random variables y of S1 so on y of Sn with joint density. The processes x of t and y of t are statistically independent. We are if all random variables from x of t are independent of those from a y of t. Thank you for give me this opportunity to me.